Howdy, calculus students. I would like to give you a brief explanation of the very powerful Alias theorem. This theorem is going to allow us to compute limits in places where the limit properties would not normally apply. For instance, I want to consider the limit as x goes to 2 of x squared minus 4 over x minus 2. If you have your graphing calculator handy, go ahead and sketch a graph of this function and compute this limit. I'll pause, actually you'll pause, while you graph and compute. Welcome back. If you did everything correctly, then your graph should look like this. That is, the graph looks like the graph of a straight line equation, and the value of that limit turned out to be 4. However, if I try to evaluate by direct substitution, it fails. The rational function theorem does not apply here because the denominator goes to 0 when x goes to 2. So no quotient rule for you. And since there's no quotient rule, there is therefore no rational function theorem either. We need something else. Now what we notice about this function that's very interesting is that for all x's except x equals 2, the function x squared minus 4 over x minus 2, which factors as x minus 2 times x plus 2 over x minus 2, is exactly equal to the function y equals x plus 2, except when x equals 2. And right at x equals 2, you probably couldn't see it on your graph, but if you go back to your graph on the calculator and you hit trace and you enter x equals 2, it should tell you that when x equals 2, y has no value at all. And that's not surprising, because when x equals 2, we end up dividing by 0, which of course is illegal. So actually, the graph has a little hole right here at x equals 2. This graph looks just like the function y equals x plus 2, except when x is equal to 2. Well, the Alias theorem is going to rescue this situation for us. We strongly suspect, based on the graphing calculator evidence, that our limit is 4. However, we don't have any way to prove it yet using our limit properties because the quotient rule does not apply and the rational function theorem does not apply either. So, we're going to learn a new theorem that is able to rescue the situation for us. And that is this. Suppose I have two functions, f and g. And they are equal to each other, except at x equals c. If these two functions are equal to each other, except at x equals c, then it must be the case that the limit as x goes to c of f and the limit as x goes to c of g are the same value, assuming that value exists. Now, how does this apply to our previous situation? Well, if we consider the function f of x equals x squared minus 4 over x minus 2, and we consider the function g of x equals x plus 2, then we saw that if I factor f and cancel the factors of x minus 2, then I get x plus 2. These two functions are exactly equal to each other, except at one point. They are equal except when x is equal to 2. the function f is not defined. It does not exist when x is equal to 2, whereas g of 2 is equal to 4. So these two functions are equal except at the single point x equals 2, and therefore their limits must be the same. And the right-hand limit here is easy to evaluate because that's a linear function, and I can do it by direct substitution. The reason we call this the Alias theorem is that we consider the function g to be an alias for the more complicated function x squared minus 4 over x minus 2. An alias is another name for the same thing. And these two functions are the same thing, except at one single point. Okay, so let's recap. The Alias theorem, which you definitely should know by heart, is that if two functions are equal except at a single point, then their limits at that point must be the same. And the example here is we have the complicated function x squared minus 4 over x minus 2, which our limit properties cannot touch. But its alias is the function y equals x, or g of x equals x plus 2, which the limit properties can evaluate for us, giving us 4. Tomorrow, we're going to spend time practicing using the Alias theorem with a technique called cancellation that will help us to make short work of limits like these.